Welcome, everyone. It's a great honor to be able to introduce Professor Michael Jordan as today's speaker. Of course, Mike is so famous that he needs no introduction, which makes my job really easy. All of you will already know that Mike is the Pihang Cheng Distinguished Professor at Berkeley. He's a member of the US National Academy of Sciences, a member of the National Academy of Engineering, a fellow of the American Academy of Arts and Sciences, a foreign fellow of the Royal Society, fellow of the ACM, the IEEE, and many other bodies. He's also won numerous prizes for his really pioneering research, including the John von Neumann Prize from the IEEE, the Alan Newell Prize from the AAAI, the HKI Research Excellence Award, the Ulf Grenander Prize from the ACM, I'm so sorry, from the AMS, the David E. Rumelhart Prize, and so on, right? And he's also given the plenary lecture at the ICM and many other distinguished lectures at the IMS. He's also been named the most influential computer scientist worldwide in an article in Science. And some of the world's very best machine learning researchers have been Mike's students and postdocs, right? Including Yoshua Bengio, Martin Wainwright, Tommy Yakola, Zubin Garamani, Andrew Eng, Eric Shing, Francis Bach, David Blay, Marina Mela, Barbara Engelhardt, Emily Fox, and so on and on. The list just goes on. And of course, not to forget our very own Professor Chiranjeev Bhattacharya from IISc. Right? And if all of that wasn't enough, Mike is a rock star on top of that. He's an accomplished drummer in his own right, and I hope we'll be able to hear him play again at NeurIPS one of these days. So today, Mike will be talking about on learning mechanism design. And I first heard Mike talk about research at the intersection of machine learning, microeconomics, recommender systems, and so on in the summer of 2018 when both of us were presenting to Satya Nadella. And so I'm really excited to hear about all the great progress he's made since then. So, Mike, a very warm welcome to you. But before I hand it over to you, just a quick word about questions and logistics. So, we've scheduled 1.5 hours for Mike's talk today. So we requested him to speak for 45 minutes, and we can take clarification questions during his talk for 15 minutes. So if you'd like to ask a question, please type it into the chat. And we have two moderators, Manish Gupta and Guhan today. So they will ask them the clarification questions on your behalf, or they'll unmute you and you can ask the question. And then once Mike's talk is over, we have 30 minutes for an extended Q&A session where you guys can ask the questions directly. But again, the questions will be moderated by Manish and Guhan. So just keep typing them into the chat, and then Manish and Guhan will select your questions. So with that, a very warm welcome to Mike. And Mike, over to you.
All right. Thank you, Monique, for a very nice introduction. It's a pleasure to join all of you all the way from Berkeley. You've reminded me of talking to at Microsoft, and Satya Nadella had invited us to talk there. And it's a good memory in particular because the message I have has to do with companies and building artifacts and new kinds of engineering. Because after 40 years of working on machine learning, I've realized what it is. It's really a new engineering field that builds real world systems. And these systems are planetary in scale, and they're involving computers and humans all mixed in and networks and so on. And that vision, maybe it's obvious. Certainly if you're in a company, it's pretty obvious. But it's pretty different from the vision that we're doing AI in the classical sense, that we're trying to put thought inside of a computer and make a computer as smart as a human being, which is an interesting aspiration. It's not what's happened, and I don't think it's what's going to happen. But it doesn't mean that machine learning isn't interesting. It's certainly interesting, but it's for a different purpose. It's really not for replacing humans. It's for augmenting human life and building new kinds of systems. So that's kind of what my talk is about at the largest level. But I am going to get into this issue about economics. And so mechanism design is a part of economics. And I think that economics perspective has been really what's missing in machine learning. And so my talk is really about that. So if you bring in economics, you bring in incentives, and you certainly bring in a social element and people's valuations. So it becomes a bit more of a social field than just the mere technical issue of building systems that learn from data. But let's return a little bit to the past. Machine learning has at least two sides to it historically. One is pattern recognition, and that certainly has been the dominant theme in the last decade. It's as you all know, systems have been built that do amazing jobs with prediction of certain kinds of patterns, and it's become a commodity. Really, anybody can do it. And the systems are good enough with human kind of data that people are excused to think that we've solved really AI problems of the classical sense, that we can imitate a human thinking. And I don't think we actually can yet. I think we imitate humans who thought in the past. We're taking data from humans and sort of interpolating over that. And it can be very impressive and look very good, but it's not really getting at the core problem of decision making under uncertainty, and thinking in the real world and living a long lifetime and making plans over long stretches of time and interacting with other people. So the decision-making side has been less focused on, but of course it's present throughout the history. And I think it's becoming more important now. It's I think where many of the interesting research problems are right now. And it has to do with not simply detecting something in an image, but high-stake decisions, life and death decisions. It has to do with understanding the decisions and making multiple decisions in the context of other people. So that's what I'm mostly going to focus on. So let's just talk a little bit more about decisions. There's, of course, a long history of decision theory, and we all think we know what a decision is. But in the prediction era, it's been thought of mostly as kind of the thresholding of a prediction. And there are people who've argued that if we can do prediction perfectly, whatever that might mean, we've kind of solved the problem of intelligence. And I don't agree. So let's think about a real world decision making problem, say, for example, medical. So you suppose you go to your doctor, and let's suppose in a few years your doctor has access to a system that has been trained on all the world's medical data, whatever that means. Just be imaginative about this. All the data from all the hospitals and all the past have been collected together and used to train a large medical model. And the doctor has access to this. So the doctor measures something about your body, maybe 100,000 variables, and puts that as an input into this big network that makes predictions. And it's really good at making predictions. No human is as good. So it predicts, for example, that you're about ready to have a heart attack. And what does that mean? It doesn't really mean that it's predicted a heart attack. It means that some number is bigger than some threshold. So the output is 0.701, and historically, if it was over 0.7, people are likely to have heart attacks. So it's a thresholding prediction of a prediction, but will you treat it as a decision? No, certainly not. What you'll do is now start to investigate. You'll ask the doctor things about what if I were to do different things? What if I were to eat differently? What if I were to take a certain medication? You'll also remember things from the past that you'd forgotten. So, for example, you'll say, oh, I remember now that I had asthma as a child, or I remember that my grandparents had heart conditions, and I'd forgotten that. And there's probably lots of things you'll remember in that moment that you'd forgotten. And now you realize that that network could not have been trained on all the world's medical data, because that's not a meaningful thing. Things that didn't seem relevant before now suddenly become relevant in the context of you thinking you might be having a heart attack. Okay, and that's going to be true of most decisions that are really important and deeply embedded in our real life. As soon as you start to realize that some test has occurred or some issue has arisen, you're going to condition on that, and there's going to be all kinds of data and thoughts and experiences that become relevant that weren't at all relevant before. Okay, so that's kind of thinking about one decision. And if you think about a doctor now in this environment, the doctor is going to be responding to questions. You're going to have a little dialogue with the doctor. You're going to say, what if experiments? What if I were to exercise more? Or what if we were to get a second opinion, and so on? And the doctor will be able to go through that. And in some ways, the doctor is running little experiments or adding new data to the old data and doing reasoning. And so that's the kind of systems we're not really building now. That's not a prediction system. That's something a little bit more. It's reasoning under the context of a important decision. Now, we're not just making one decision in our life. We're making large numbers of interlocked decisions over a span of days or months or lifetimes. And they're all interacting with other people's decisions too. There's information links. For example, if you get a new medical treatment and it works, that then flows to other people to change how they're being treated. If we're doing transportation, one car going down a road has impact on other people. And all decisions in the real world interact with other people. So there becomes scarcity issues, there becomes trade-offs and so on. So now we're starting to get into economics issues, and machine learning systems should be responsive to that. They should understand those economic issues, and they should understand interactions and scarcity and so on. And currently they just don't. We put machine learning systems out there and they either sort of work or they don't, and we're trying to then fix them after the fact. And so this becomes clear when you start to think about recommendation systems. These are part of the success story of pattern recognition systems in machine learning. They look for patterns in people's purchases and they make recommendations. So you could think of this as decisions. They're trying to make you make a new decision to buy something, but we don't really treat this as decisions. We treat it as some kind of advice in some context. Okay. And moreover, these systems are not built for one person. They're built for millions of people. And when millions of people are using them, there really is now a network of decision making going on. All right. So in the classical recommendations, they were, for goods that were not scarce. So, for example, you could recommend movies to people. And if you recommend the same movie to large numbers of people, maybe to 1 million people, I'm sure that happens on Netflix every day, there's no problem. You just copy the bits. If you recommend the same book to large numbers of people, no problem. You can copy the book now very quickly. But if you start recommending goods that are scarce in the real world, like restaurant seats to people, you could recommend the same restaurant to 10,000 people, and that'll create congestion. And you can recommend the same street to large numbers of people, and that'll create congestion. And so this seems like an easy problem to fix. You just say, okay, I'm not going to do that. I'm going to make my system load balance. It's going to only send 10 people to each restaurant. But now the question is, which 10 people? And it can be just arbitrary, and it can't be because you know something about the people, because you know their browsing history, or you're snooped on their lifestyle or something like that. It really needs to be that you involve the person at that point. It's like a market. They have preferences, and they may in the moment have thoughts about what they'd like to do. Maybe they don't want to go down the fastest route because they want to go visit somebody, or they want to explore some part of the town they've never seen, or they don't mind going a little slower today because maybe then tomorrow they get to go faster, and so on and so forth. So this is like when you enter into any rich situation like markets. Suppose you go to a thriving market in Bombay, Mumbai. You're going to walk in there and there's going to be all kinds of opportunities and all kinds of interactions that you never thought about before. But in the moment, you're going to react and you're going to interact with other people, and something hopefully good will come out of all that. And we're very good at that kind of thing. All right. So the alternative to creating a pure recommendation system in these situations is to, in fact, create a market. So for the restaurant example, it's really natural. You say, on one side, there are consumers, people who would like to eat a dinner. And on the other side, there are producers, which are the restaurants that have seats to offer. And you're trying to create a matching between those two sides of the market. And each restaurant may have certain different things to offer, and each person has different things they're interested in. And in the moment, they should be able to find each other. And so an app should actually have two sides, and there should be interactions and matchings going on as the app is running, not just giving a list of recommendations to people. There should be bids going back and forth. There should be money involved, and so on and so forth. And this isn't only true for restaurants, it's true for all kinds of things. In particular, Monique alluded to my interest in music. Music is really broken in the current era. We think of computer science as creating streaming services that have made music go everywhere, and that's wonderful. But in fact, there are not many jobs in the music industry. And it turns out that if you look at the data, most music being listened to today, on any given day, anywhere in the world, has been made in the last 6 months, and it's been made by people you never heard of, often 16-year-olds to 20-year-olds who are just really good. They have a laptop and they're able to create new music. And most of them don't get ever famous, and their music gets streamed and listened to a huge amount, but they never get paid for it. So this is really broken, and this is kind of like a recommendation system. The streaming service is just recommending songs, but the songs are free. And then the intermediate service creates an advertising or subscription program to make money for themselves, but they didn't make money for the artists. They're not actually building a market. All right, so there's a way around this, and it really involves simple machine learning, if you will, but with a different mindset. You're trying to link producers and consumers. And so there's a company in the United States. I've actually been involved. I'm on their board. It's called United Masters, and it has now over 2 million musicians signed up. Those musicians are connected to the other side of the market. They know who their listeners are, and moreover, they're connected to brands. So if you go to the NBA website and watch a clip and hear some music, that music is from these United Masters artists because Steve Stout over here, who's the CEO, signed a contract with the NBA. And whenever a song is played, the artist's music is streamed and the artist gets paid in that moment because their music has been listened to. So they're making a salary. And so there's now 2 million people who are making money by making their music in a market environment. And this could be done without large-scale machine learning because you're learning about who's listening to what and what's popular and bids are going and it's an auction and so on. So I can imagine doing this. This is being done in the U.S., certainly in India, in Brazil, China, et cetera, throughout the world, really, Africa, where people are making music and they want to listen to it, and there should be a connection between producers and consumers. And it doesn't have to be just for music. It can be for all kinds of other services and goods. And machine learning people just haven't been thinking this way. Others have, but machine learning people have not mostly. Now, if you're a machine learning person, you'd like to do algorithmic and mathematical kind of things. Are there new problems that come when you link machine learning with microeconomics? And the answer is absolutely. There's all kinds of new problems, and they're really interesting and complicated. And to me, the most exciting problems I've ever seen in my entire career. So just the first one really briefly is, optima is what we're trying to find in machine learning. We go downhill until we find an optimum. In economics, you don't really believe you can ever find optima. What you can do is find maybe equilibria. But in economics, the equilibria, you don't think too much about how you arrive at the equilibrium. You don't think about the dynamics. And so, there's some of that, but just not nearly enough. So bringing these two mindsets together, well, three of them really, you want to have dynamical systems that are good at finding equilibria. And there needs to be a sort of a local notion of, equilibrium and optimality. So, best responses and so on, all done adaptively as data is being collected. So there's all kinds of brand new problems just in that one bullet. I've already alluded to some of these market building exercises. If you go further down my list there, like uncertainty quantification, we're still not doing that very well for classical machine learning. If you try to do that in the world of market building, it's terrible. It's really critical that you solve uncertainty issues because you have to make decisions. And if you have to make decisions, you have to have uncertainty. We're going to talk about mechanism design today, which is how do you build algorithms that learn preferences and then help people make good decisions in interactions. We'll talk about contracts and then incentives. Anytime you bring incentives into the picture, you're doing economic thinking. And if you do that with data, you're doing machine learning thinking, and putting the two together is really important and interesting. All right, so to me, the overall goal is to solve the problem of building learning-based markets that are stabilized over long stretches of time. And when I say long stretches of time, I mean, not just days, but months and years. Markets often will work over months and years. They adjust to the environment, to the weather changes, they adjust and so on. They're healthy and adaptive in some ways that our current machine learning systems really aren't at all. So bringing ideas from economics is very promising in that regard. Okay, so the second part of my talk, or the rest of my talk, is going to be a few little research vignettes to show you some of the conceptual and then algorithmic and mathematical ideas that arise when you start to study these kind of problems. I've just picked 4 from my group in the last several years. If you go to my publications page, you'll see a whole bunch of other ones. It's a very active area for me. I've just picked ones that I think are really interesting, first of all, because they're brand new, and second, because they're open. There's lots of brand new problems. And also, they bring in some key way an economics idea together with a learning idea. Okay, and really foundational links between these two fields. Okay, so let me start with the area.
Professor Mike,
Yes?
before we go ahead, there are a few questions.
Oh, please, yeah, it's a good point. Please.
Great, thank you. Manohar, maybe you can go ahead and ask your question. Manohar Swaminathan.
Yes, thanks. Mike, I was just wondering if UnitedMasters.com is similar to many other sites what are called creator economy. For example,
Yeah.
Patreon.com connects lots of creators directly to the patrons, and they contribute and they get benefits based on their patronage.
Yeah. Yeah, so just let me be clear. Thanks for asking that question. It's really good. Creator economy is something I really like, that phrase. It's a Silicon Valley buzzword, but that's one I really like. And what I'm saying is really not that new. It is kind of in some sense the creator economy idea. And what I'm just trying to argue is that the machine learning people have a role to play here. It's not just building the platform. It really is also the data analysis and the incentives and the possibility people aren't telling the truth and the evaluations of people's utilities and all those things that machine learning people, if we start to talk that language, we'll be able to help build those kind of systems. So you're right, United Masters is an example of creator economy, absolutely. It just happens to be a successful example. And that's partly because the CEO is a real human being who went out and sold, wrote contracts for people, approached the NBA and connected up this market. And so people who are entrepreneurial, it's not enough, I think, in this era just to build a platform and have a nice idea and then hope that people will come to it. And so, in fact, a lot of these companies are doing that, and not many of them will succeed. United Masters, I think, is a success story at this point. It's been going for 5 or 6 years. And it's getting to arrive at scale. So part of this is actually a business school side of the talk of how do you actually build a company that does the creator economy. And certainly machine learning is critical. I would say it's necessary, but not sufficient.
Thank you.
Amrit Sahu, can you unmute yourself and ask your question, please?
So the problem you mentioned with restaurants and streets with prediction system is that they are getting congested or one restaurant is getting filled up. That can even happen with books and movies, right? It is just not visible enough. But then some kind of books are more often recommended and that the competitors lose. Hence, same goes with the movies also, right? Happens in all aspects of the recommender systems.
Yeah, no, you're absolutely right. Scarcity really is everywhere. And I was just trying to caricaturize in some ways the classical mindset. But, even you're right, it's scarce. But when you think about books or movies, it's not really too big of an issue of who gets the book if you don't have enough of them. You kind of send it to the first person or you kind of randomly choose and, it's okay. But if you are making decisions about who gets to go on the fastest route or who gets to go to the restaurant, we're not so comfortable with just random choices, right? Because people really do have strong preferences. And moreover, if you ask my preferences in the moment, you may not know that I love Indian food, for example, which I do, but maybe I've not gone to Indian restaurants the best, but I really do like it because, my friends make it. And if you put me in the situation where you offer that to me, I'll accept it. Yeah. So in Silicon Valley, people will say, okay, why do I need to to give you the opportunity to pick to have options for a restaurant to go to in that moment? What I do is I know a lot about you. I've seen in the past, you've always gone to Chinese restaurants. So I'm going to connect you to a Chinese restaurant. You're not going to mind. But no, maybe in that moment, I really want to, I don't want to be going to a Chinese restaurant again. So you can't let the platform decide in the case of real world goods because people really care. Whereas for books and movies, if the platform decides, it's not so terrible. So that's the distinction I'm trying to get at.
Okay, thanks.
Okay, so strategic classification. So this could be a problem where you're gathering data, but you're gathering data from people, and people may not give you the true answer. So that's what's called strategic classification. So this happens all the time, and this is also not a new problem. It's been worked on for maybe 5 years now, but it's not widely worked on. So imagine that I'm a health insurance company, and I want to offer you insurance, and so I'm going to have to price it. And obviously, I'd kind of like to have a cheaper price for people who are in better health. So I'm gonna have you fill out a form, and you're gonna say something about your health. And obviously, if I ask some question about how often do you drink, you're gonna probably give a smaller number than you really do, or how much exercise you do, you'll give a bigger number than you really do. That's just human nature. So what's happening is now the health insurance company is getting biased data. And if they build a classifier from that, obviously they're going to get a biased classifier, and it's going to be biased in maybe unforeseen ways. And but that people, if you ask a certain kind of question, will give a certain kind of answer. It's part of the overall your expectation. So you should bring that into play when you set up the classifier. And so this is well known in economics. In fact, this is called Goodhart's law, that if you put up any kind of measure that people care about the outcome. So here's one called the Poverty Index Score. This was in Columbia in 1994. People defined a new score, and you see a nice Gaussian curve. And by 2003, on the lower right, you see that the entire curve is shifted, where most people are just below the poverty line. And of course, they did this because they got more benefits from the government. So people are now lying when they supply data because they get more benefits. And so you can imagine this is just going to happen all the time. So in fact, in general, we're going to have feedback loops in learning when we gather data from self-interested agents. So here we have a game. On the one side, the strategic agents are imagining the model that's being built, or maybe they know something about the model because for regulatory reasons, the decision maker has got to reveal it. But in any case, they have some idea of the model, and so therefore they change their data. They give strategic data to the decision maker. And in economics, these are called Stackelberg games. This is a repeated Stackelberg game. Stackelberg just means it's done in sequence. That one side of the game makes a choice of an action, the other side does a best response to that, and then you iterate this process. So this is an unusual Stackelberg game in that it's statistical. So on one side, the best response is to supply data. On the other side, the best response is to build a model. And so maybe you think of a bank that's collecting data from people about and trying to decide whether people should get a loan or not. And so again, the people are now motivated to give false data so they have more chance of getting a loan. But the bank knows that, so when it builds the model, it hopefully takes that into account. And moreover, in this setting, the agents are probably going to require to know something about the model. Maybe they won't know all the coefficients, but they'll know something about maybe it's logistic regression, or they'll know something about the kind of features that are being used. All right, so now the question becomes not of optimizing, but of finding an equilibrium. Is there an equilibrium of these kind of games? All right, so Stackelberg games have a leader and a follower. The leader is the one who goes first, and the follower goes second. In repeated games, you can also have a notion of leader and follower, and it has to do with the dynamics. It has to do with how fast one side of the game is acting. So a typical analysis of these things assume everything is synchronized. So here you would have the decision maker making a model at time t-1, then the best response would come either just before or just after that from the agents, and then that would iterate at the next time step. All right, but in real life, there's no reason that things should be synchronized. Agents, like humans, are going to do whatever they do at whatever time scale they do, and the bank will do their own thing too. And so really the better way to think about this is that the timescales are decoupled, and to imagine two cases, one in which the agents are very fast, like here, and the other in which it's the other way around, the central decision maker is very fast. All right, so do these happen in real life? Well, here's the one where the agents are fast and the central decision maker is slow. Okay, so the decision maker waits for a while until it builds a new model. So does this happen in real life? Well, definitely. So for example, college admissions, they're collecting applications from people, but they're not changing their admissions policy after each application. They're waiting maybe a year or two before they start to change their policy for obvious social reasons. Credit scoring is the same kind of thing. All right, so that's a real-world Stackelberg game when the agents are being very much faster than the central decision maker. On the other hand, you can imagine the other way around, where the central decision maker is very fast and the agents are slow. Well, does this ever happen in real life? Well, definitely. This is more the classical IT paradigm. So YouTube, for example, is gathering data all the time. Every time anyone has an interaction, they will, in principle, update their model. And then the model evolves very, very quickly, and everyone accepts that. Okay. All right. So now you have two different Stackelberg games here. And you can ask, are there equilibria in these games? And are those equilibria, first of all, are they different? If they're different, are they more favorable for the central decision maker or more favorable for the agents? Right. And it turns out when you do the analysis that in the situation like we show here, where the central decision maker is very fast, it turns out the equilibrium, there is an equilibrium, and the central decision maker has a lot of welfare. Okay, their utility is very high, or their regret is low. Whereas for the strategic agents, their utility is not good. It's bad. Okay, so they have low social welfare. All right, so now you might ask, what happens when you turn it the other way around? And so we have done that theory, and I'm going to show you the results on the next slide here. All right, so here the first result is simply shows that both kinds of dynamics give you equilibria. All right, so that's not that hard to show, and it's not that surprising. The second theorem, though, is surprising. It shows that when you turn it around and you let the strategic agents go very quickly, not surprisingly, they have higher social welfare in the equilibrium that arises. But very surprisingly, the central agent, the central decision maker, also has higher social welfare in that situation. So this is a kind of rare example in game theory where there's a win-win, that under one particular equilibrium, both kinds of agents are more happy than they were in the other kind of equilibrium. And the other kind of equilibrium, the central decision maker was reasonably happy, but the agents were not. And here, both kind of players are quite happy. All right, so that just hopefully gives you a flavor. This is game theory, really, analysis of equilibria, but done in a statistical setting where we're modeling data and people are providing data. And so the results are not standard game theory results, they are statistical game theory results. So I'm going to stop on that particular talk. There's lots more work going on that topic, and turn to a second topic. This is about multi-arm
Professor Mike, is this a good time to ask questions?
It's another good time. Yeah, I'm going to give these 4 little vignettes, and they'll get a little shorter, each one of them. And after each one of them would be a perfectly good time for questions.
Yeah, so with regards to those equilibria, can you describe, give an example of what these equilibriums mean? And in particular, do you assume all these agents are similar or they are of different types? And is this equilibria with respect to each agent, or is it like to the group of agents? What can you please describe? What does that mean?
Yeah, it's equilibrium with respect to the total social welfare. So it's a sum over all the agents. The best response function is, it's an equilibrium with respect to best responses. So there is a best model to build, and there is a best set of data to give. Now, one thing I didn't say is that there has to be a penalty for the agents to when they falsify their data. So they have a true data point, and they don't want to reveal that. But let's imagine it costs them a little bit to fake the data. And so we have a ball around each data point which reflects that cost. So imagine that instead of simply asking you how much you exercise, I require you to show that you paid to go to a gym, for example. So you had to actually show me that you spent money. So that's a little cost that you have to incur. Or maybe I record accelerations on your cell phone. That's a cost that you have to bear of loss of privacy. But in any case, we're going to imagine that part of the game involves a cost that the agent has to pay to if they move their best response too far away from the actual original data. And so there is an equilibrium which has to do with how far you move in that ball. And then the model itself is a regularized model fitting problem. So there's kind of a regularization on both sides, and that the equilibrium is expressed in terms of the regularization.
Thank you. Meenakshi Sarkar, maybe you can unmute yourself and ask a question.
Good morning, Professor Michael. So my question is, these games that we are talking here, they are thought to be non-cooperative, right? Or cooperative?
They don't have to. I mean, most game theory is non-cooperative. You're going to see some more cooperative game theory here, but really, the cooperative and non-cooperative are not that different, just to sort of maybe say it that way. But so the games here don't have to be non-cooperative.
Okay. I had another question from the previous portion of the slide. Should I go ahead, or it would be fine?
Sure, no, go ahead. It's fine.
Yeah. So I actually wanted to know that this relationship between this optimality and equilibrium. So I actually wondered that why, like right now, people are wondering how these two are connected. Is it because that previously when we were doing this pattern recognition tasks with machine learning algorithms, the concept of equilibrium did not exist because we are not dealing with dynamical systems. Now, as we move with dynamics, so now these things are becoming more relevant, and Lyapunov theory is making a comeback in the learning, paradigm. Is that what is happening? Just
no, it's not that. We've had dynamics for quite some time, and we're very good at rates of conversions of dynamical systems to optima. But what equilibria are more like fixed point problems. So imagine a dynamical system, a vector field, which is a bunch of circles that I have arrows going around a circle. And I do that at all scales. All right. So there actually is, if we were to follow the vector field, you would just simply go around in a circle. You wouldn't converge ever. Okay. But that vector field is the vector field for a zero-sum game. So there is a fixed point, which is in the middle, where everybody's happy. It's a Nash equilibrium. All right. And so the dynamics here we're talking about is the dynamics of fixed point algorithms, which is not the same as the dynamics of descent-based algorithms. And in fact, if you do gradient descent on that vector field, you'll follow an error, you'll go a little bit outside of the circle, and then that'll happen again at the next step, and you'll diverge outward. So gradient descent completely fails, but there are known algorithms like extra gradient and optimistic gradient, which will actually converge to the fixed point. They'll spiral in that kind of situation. So it's a new kind of, it's a not new, but it's a different kind of dynamics than we're used to in machine learning. It's equilibria finding dynamics. And what's going to be new, though, is these will be stochastic dynamics because of the learning. We're gathering data, so everything is random. And so that's the kind of thing that you haven't seen very much of in economics.
Thank you, Professor.
Naveen, please go ahead. Naveen, go ahead.
So the theorems that you described, can they be tested in practice?
Good question. I don't want to kind of give too facetious of an answer, but these kind of theorems have been around since Nash and Stackelberg, who were working in the 30s and 40s, right? And what people liked about their kind of equilibria was that they were descriptive of the kind of things you would see in the real world in some cases, but not all cases. So Nash equilibria in particular are often criticized by economics people. You don't see them often in real life, and often there are multiple equilibria. It's not clear which one is best. Stackelberg are more common as a good explanatory principle. But there, one has got to now do actual experiments with behavioral economics and set up real life experiments and test things and then do the mechanism design to try to say, well, I don't like that equilibrium. I'd like to push it in some other direction. Does my mechanism also work? So I spend the day a week at Amazon just to say, and a lot of what I'm saying right now is informed by my experience there more than my academic experience. I watch actual markets and new mechanisms be proposed, and then experiments are done because you have the resources of Amazon. You have millions of people coming in every minute to do transactions, and so you can pull out some and test, run an experiment and test a mechanism or test a whether you have an equilibrium. If you perturb away, you return to the equilibrium, and so on. Again, I'm at the end of this. I'm going to say something about this is a new engineering field that's emerging. It's going to take decades to do, and it's going to take also decades for our academic research to be able to do really meaningful experiments. We're going to have new kind of test beds. We're going to have new kind of behavioral experiments being run. It's not enough just to gather a very large vision data set and run algorithms against it. We're going to have to worry about new kinds of test beds. So just to say that there's not an easy answer to the question. Obviously, when we design this kind of particular game, we look at real data. We've been looking at loan data, and I'm going to talk in a minute about drug discovery data. And we're kind of guided by that. We know our current algorithms will fail, and we're designing something we think is better. But then a lot of work has to go into testing it.
Thanks, Rob.
Mike, this is Manik. Can I also ask a question?
Yeah, please.
So I just wanted to understand this from the perspective of computational advertising. If you look at marketplaces like Google or Bing or other search engines, they've been building two-sided marketplaces for decades where a lot of these things are true. The advertisers would not want to reveal their true bids and so on. And we still have to build models that will take this into account and provide long-term user satisfaction. So have these problems not been studied in computational advertising, or solutions come up, or are they somehow inferior?
Yeah, you're going to see in the rest of the talk something about that. Just to say it very quickly, though, first of all, those are mostly auctions. They're almost entirely auctions. And auctions is one narrow part of mechanism design. I'm going to tell you about contract theory in a minute, which is much broader, and I think is more relevant to real normal people. Whereas auctions were kind of relevant to a very, to marketing campaigns. And then secondly, just as a more sociological note, I'm not very happy that Facebook and Google, built these marketing-based ways to sell basically products that all of us made. You made a website or you created some video, and they then made money off of advertising, but they didn't include you in that. And really, I like this creator economy much better, which is that somehow the producer was the person who made the thing. And, the platform should just be, the market maker. It shouldn't be the person who makes the money by creating a false market, a different market between itself and advertisers. That's what Google and Facebook did. I actually, just to kind of distinguish between the companies, I think that Amazon and Microsoft are different. I think they're more in the game of creating producer-consumer relationships. Certainly Amazon, they bring packages to your door. And so people who made the product, their product is being delivered, and you're paying the person who made the product. And Amazon is acting more as a market maker in the middle. This is a little bit of a caricature, but just to say, yes, advertising is certainly a mechanism, but I just don't think it's been very healthy. And I want us as machine learning people to explore a wider set of mechanisms that are a little bit more in this creator economy side and less in the big company makes money side.
Thank you.
Hey, Professor Mike, I had one question. So if I relate this to the earlier part of the talk, right, where you were talking about creator economy, in these cases, like the value may not be known, right? Because you are still discovering and are in the process of recommending new items to the agents.
That's right.
How is, like, for calculating the welfare, right, and optimizing it, you need to know the value, right?
Okay, so that's my next two parts of the talk. So let me go ahead and move on a little bit. Let me do the bandits, and then let me do the contract theory, where I really think you'll start to see this. Let me just maybe move through that. That'll maybe take 10 or 15 minutes, and then I think we'll have more to talk about. So in fact, this next section is really one answer to that question about what if you don't know the values a priori. Okay, so this is with Lydia and Horia, who've been students with me at Berkeley. And so you all know what multi-arm bandits are. This is where there's actually a value to pulling each of the arms, but you don't know the value. So, a human comes in and they say, I'd like to get a reward. So I pull the first arm and I get a certain reward. And I don't know the distribution, but I'd like to optimize the mean reward. So I've got to explore a little bit to find out what are the rewards I get out of each of the arms. And hopefully all of you know there's a huge literature on this now. And what you do is you don't learn the whole distribution, but you learn confidence intervals on the mean rewards. And so here's just the classical UCB algorithm. It samples each of the arms a certain number of times. It forms a classical confidence interval for the mean reward, and then it selects the next arm according to which arm has the highest upper confidence bound. So here the second arm has got the highest upper confidence bound, and that tells you that either you're very uncertain about that arm, and so you should pull it for exploration reasons, or that it's an arm with a high reward, so you should pull it for exploitation reasons. So hopefully you all know about that at least a little bit. So here's a case where one decision maker is trying to find the best action and it doesn't know the value a priori, so it explores and exploits. And you probably know there's a notion of regret, that if you compare yourself to an oracle who knew the optimal arm a priori, that there are algorithms that can learn with regret that's logarithmic with respect to the amount of time relative to that oracle. And so the UCB algorithm is a particular example. All right, so that's on the learning side. It helps us think about situations where we don't know the value a priori. Now on the market side, what if we have multiple buyers and multiple sellers, not just one agent learning? Well, matching markets are a classical mechanism. So you have buyers on one side, sellers on the other. And in the classical literature, you assume that you know the preferences of the buyers and the sellers. So buyer number one prefers seller one to seller three and prefers seller three to seller two. And you assume these are all written down a priori. So this is natural in some cases, like college admissions. All of us have to say which college we prefer, and we write down a list in some sense. And the colleges have criteria, what kind of student they prefer and so on. And now there's algorithms like deferred acceptance, which there was a Nobel Prize given for it, which match buyers and sellers so that the overall system is in equilibrium. It's stable. It's not optimal, but it's in equilibrium. Okay, now, so obviously the question arises about what if you put the two together? What if I have now a matching market, but the agents don't know the value of the arms a priori? So you're trying now to match the bear and the human to a good choice of arm on the other side of the market, but they don't know what the best arm is a priori. And there's scarcity. You can't have the two both pick the same arm. All right, so suppose that in fact at some point they're picking arms and they're getting rewards and they pick the same arm. Well, in our model, we modeled economic scarcity. So we assume that only one of the agents gets a reward, here the bear, and the other agent gets no reward. Now, who gets the reward? Well, arm two has preferences on the other side of the market. So arm two, for some reason, prefers the bear. And so the human looks at that and they say, oh, I see. I like arm two, but arm two prefers the bear to me. So if I pick arm two, I'm likely to lose. So I should explore the other arms more than I otherwise would. And that last statement suggests there'll be a higher regret because I have to do more exploration when there's competition in the market. So that's a nice mathematical question. If there's competition, do I have higher regret or not? All right. And so just to say it quickly, what we studied that, we define this now notion of a bandit market in this paper, where it's basically just exactly what I said. We get noisy rewards, but there's multiple agents now competing. And we define a notion of regret in this market, which is basically the amount of reward you get relative to an oracle that knows the best match a priori. We define a particular regret minimizing algorithm that's basically UCB with deferred acceptance. Okay, it takes the current upper confidence bound and it uses that to match on. We call that the GS-UCB algorithm. All right, and then finally we proved a theorem which proves here's the regret. And so the regret is in fact still logarithmic. So that was a surprise. You don't lose in terms of the logarithmic regret, but you do lose in there's a denominator term, which is the gap between the probability of payoff of the different arms. All right. So again, if these two agents have high overlap, both of them like arm 2, then there'll be a small gap, which will lead to a bigger regret. So there is a loss. There's more regret if there's competition, but it's only a constant, and it's something we can characterize. Okay, so again, I'm going to move on to another. There's a whole now emerging literature on bandits with this kind of competition, market-based competition. But now probably this is the most important part of the talk. This is the most recent part. This is what we're calling now statistical contract theory. So contract theory is a different kind of mechanism. There's auctions, which you all know about. We're not going to talk about here. There's matching markets, and then there's contract theory. There are others, but those are the 3 main branches. So this is with Stephen and Michael and Jake, colleagues at Berkeley and at Stanford. And let me just again summarize a little bit. The theory of incentives in economics, which is how do you kind of build the mechanisms that deliver good games, that have good equilibria, have multiple branches, and contract theory is one of the branches. So in contract theory, agents are assumed to possess private information, and there's a central principal who wants to incentivize them to take good actions that'll make either the principal happy or the agents themselves happy. But the agents are not willing to reveal this private information. Okay, and so you all know what this is. This is very common. So if you take a flight, there's not one price to get on an airplane. There are multiple prices, and you might think that's kind of crazy. Why is that? But now you realize that it's very hard if the airline sets one price. Suppose that you're traveling, from Mumbai to Paris, and there's some people that really want to go. That's really important to them to go to Paris, so they would pay 2,000 euros, no problem, or they're just rich. So if but there's other people that would never pay a price like that. So if the airline sets a price, that's too high, they'll only get a few people, these rich people. If they set it too low, they'll lose all the money they could have gotten from the rich people. So you know what they do? They want to set 2 prices, but they can't just do that by asking people, are you rich or are you poor? Or how much do you want to go to Paris? And they'll make you pay more. That wouldn't work. So what they do is, of course, they make they make a menu of options. And they say, if you pay a lot more money, we'll give you a special glass of wine, and we'll give you a slightly bigger seat, and we'll let you get on the airplane first. And unbelievably, there's some people that are willing to pay, thousands more dollars to have a little glass of wine and have a little bit bigger seat. And so those people are very happy. They get this special treatment. And the people now who don't do that, they pay a lot lower fee, and they're in the back, and they're also very happy because they didn't pay all that money, and they still got just as good a flight. So everybody's happy, and moreover, the airplane is happy because all their seats are filled. And so you can now make mathematics out of this. And there's a theory called, theory of contracts that sets up the kind of menus that will give you optimal welfare, that the plane is full and everybody is as happy as they're going to be, without ever transmitting the information about whether you're willing to pay a lot or not. That information was never transmitted. You just gave an option, and everybody had the same limited options, and they were allowed to make a self-selection. All right, so that kind of way of thinking can also come into machine learning. And here's an example. So let's imagine we're doing drug discovery. So in the United States, there's something called the Federal Drug Administration, big governmental agency, and it's trying to decide which drugs go to market. And they run something called clinical trials to do that. And here's a list of some of the clinical trials that have been done in the last year. And you can see that for all these different kind of therapeutic areas, cardiovascular, dermatology, and so on, tens of millions of dollars are spent to run clinical trials. And so, why do you have to spend so much money? Well, you have to have pretty big clinical trials to get a good, error rate. Not many false positives and not many false negatives. All right, and it costs a lot because you have to have a lot of people in those trials. All right. Now, if you ask, could you do this more cheaply? Well, you have to ask about what kind of tests are being run here, and what's the false positive rate, and what's the false negative rate. And so now you're asking a statistical question, and the FDA is full of good statisticians. And so what they do is they think about this a little bit. Okay, it's a hypothesis testing problem. The Neyman Pearson algorithm, approach is optimal. So if it's a bad drug, theta equals 0, meaning it's not an effective drug, then let's set up a test so that it's a probability of approval is 0.05, 5% false positives. If it's a good drug, let's make sure the test approves them with 80% probability. That's the power. And that's a good statistical profile. In fact, it's optimal. All right. But now if you go back to this picture here, you also have to ask about where are these drug candidates coming from? The FDA is not designing the drug candidates. They're coming from the agents who are the pharmaceutical companies. And the pharmaceutical companies are happy to send, thousands of drug candidates to the FDA and hope that some of them get approved, even if it's a false positive. Because if it gets approved, it goes on the market and they can make, hundreds of millions of dollars. And even if it's not effective, that's okay. They make a lot of money, and then someone else eventually gets a better drug and they drop out of the market. But for a while, they made a lot of money. All right, so the FDA has a problem. They'd like to ask the agent, what do you think your drug is really good or not? Because the agent, of course, will know a little bit internally. They maybe did an internal test, or they put their best engineers on the problem, and so on. So they know, but they're not willing to tell the FDA, yeah, I think my drug's a good drug. They just put all their drugs out there and hope that some of them get through. All right. And so in particular, if you go back to the statistical protocol here, if you now look at two different cases, one, a small profit. What if it costs $20 million to run the trial? And what if you're approved, you make 200 million? So it's, it's a very niche drug. If you now do a calculation of the expected profit, given that it's actually a bad drug, which no one knows, but you could do the math, it turns out the expected profit is minus 10 million. So of course the CEO of the drug company will say, oh, that's terrible. I'm not going to send lots of drug candidates in. Only if I'm really sure it's a good drug will I send it in, because otherwise I expect to lose money. Look at now case 2, where it still costs $20 million to run the trial, but if you're approved, you make 2 billion. And so that would be for a drug like, ibuprofen or something. And now if you do the same mathematical calculation, you can see the expected profit, even if the drug is not effective, would be 80 million. And so now the drug companies are incentivized to send in any drug that seems at all plausible. And that's actually more what's happening in our modern real world. Agencies like the FDA are getting flooded with candidates, and they're having to run these very expensive clinical trials, and they're still having lots of false positives, and the system is pretty much broken. All right, so I hope you can sort of see that this is an example of contract theory. It's like the airlines. You can't ask people whether they have a good drug candidate or not, just like you can't ask people how much they want to go to Paris. But you can set up a set of options for them, how much you pay, and then how much profit you can make. And so we've done that now. We have a new theory. We call it statistical contract theory. And just briefly, and I'm going to finish up here pretty soon. Briefly, a statistical contract looks like the following. You have the agent, if they want to play the game, they can opt out, of course. But if they opt in, they have to pay a reservation price R, some amount. And then they choose a payout function, which is going to be a function of the clinical trial outcome, and then how much of a license they're able to get, how much profit they're going to be able to make. So they get to choose their payout function. And of course, they'll choose it based on their private knowledge, but everybody gets the same set of choices. Now, then this is what's new relative to the economics literature. You run a statistical trial, which means you collect data and you do an analysis. So that's Z is the data. And now the agent gets a payoff based on their choice, f of z, and the principal receives a utility, which depends on f of z, which is how much they're going to have to pay, but also depends on the true state of nature, theta. Because if the FDA approves lots of bad drugs, eventually the FDA is going to look very bad, and they don't want that. So that's their utility has to also depend on theta. All right. So that is statistical contract theory, and now we've been able to prove some theorems characterizing what optimal contracts look like. So what kinds of lists of statistical tests are possible if you want to do contract theory? It's not arbitrary statistical tests, but it's a special class of statistical tests, or statistical classifiers, if you will. And I'm going to do this in 2 slides. If you want to see this, we have a paper about this. You can see more of the detail. But basically, in any incentive problem, you have to talk about what incentive alignment means, what it means to be incentive compatible. And so here, just if you look at that gray box, you'll see that the expectation under the randomness, if the drug is not effective, meaning you're using p theta 0, of the amount you have to pay minus the reservation price has to be negative. Okay, so this is the agent's expected profit. And if that's strictly positive, then the agent is making money out of nothing, and the FDA would never do that. So that would be not an incentive aligned. Okay, so we call this the incentive alignment story. All right, and now we're able to prove a theorem, which you see at the bottom there, which I can't really explain in this short talk, but we have an if and only if theorem, that a contract is incentive aligned in the way I just said, if and only if all payoff functions are e-values. All right, so an e-value is defined at the top of the slide. If you know, these are kind of new concepts in statistics. If you know what a p-value is, it's a tail probability on the null hypothesis. An e-value is like a martingale. It's an expected value being less than or equal to 1 under the null hypothesis. Okay, so it's kind of like a non-negative martingale. It's a sub-martingale. It means it goes down. So it's bounded above by some constant. Here, take it to be 1. All right, so even if you don't know what an e-value is, just kind of know it's a measure of evidence against a null hypothesis. It's related to p-values, but it's in some ways better than p-values. It allows you to combine things in a neater way, and it has a more of a stochastic process interpretation. But it's evidence against a null, and it turns out that we proved that the set of statistical contracts is the same as the set of e-values. Okay, so that gives us now tools for designing statistical contracts for all kinds of problems, and we've been starting to do that. And so one example we've been doing that is in the domain of federated learning. This is with Praneeth Karimareddy, who some of you may know. So you all know, here's kind of some pictures off the internet of federated learning. We've got a bunch of agents who are supplying data to a central server, and mostly people have not been thinking about the incentives problem of here. Why should the agents send the data in? What's in it for them? Don't they worry about loss of privacy? Why do they care about the central agent getting a good model? And so if you add the incentives to this problem, you start to ask about the problem of incentivizing data sharing in federated learning, and that's the problem we've been addressing. So you'll see a paper there at the bottom with Praneeth, Winchell, and myself, where we use this contract theory idea to incentivize data sharing in federated learning. And so this is kind of a new way to think about economics mechanisms in the federated learning setting. Okay, so I'm not going to provide details here, but basically, but let me just say a little bit more about what the problem is. The problem is that if one agent is supplying data and they know another agent is supplying data, they could free ride. They can say, well, that agent's providing all the data. If I add any data, it's not going to do much better, so I don't have to send anything in, and I'll still get the benefit, associated with the overall federated learning problem. And so to avoid that kind of free riding, that's what contract theory allows you to do in classical economics, and here we're doing it in the learning setting. Okay, I'm going to finish there. I have another part of the talk which I'm actually going to skip, but just to say, if you're interested in this, we have a bunch of papers on this. This is uncertainty quantification, and we're using these kind of uncertainty quantification ideas throughout all of this work because we need uncertainties to do economics, and we need uncertainties to do learning, and we certainly need uncertainties when you put the two together. So we've been working with these conformal prediction ideas to do uncertainty quantification. You can see my co-authors there, and maybe I'll just show you kind of a couple of pictures real quick. This is a way to do uncertainty quantification where where you don't have to change the model at all. So you take a black box like a neural network, you add a calibration layer to it, and you can now give out confidence intervals, which are actually correct statistical confidence intervals, without changing the network at all. You're just kind of calibrating the output of the network. And just to show you maybe this running on a real world problem, this is visual object recognition, where the entities in the scene are being labeled, not with a single object label, but with a set of labels. And our theory says that the true label is in the set with probability 95%, or whatever value you choose to. So this is real statistical uncertainty quantification, meaning we can guarantee the truth is in a certain set, and you can see how uncertain you are by how big the set is. And if it's a small set, you can see what the the object label itself is. So this is running on the usual. This is the usual vision pipeline done on real world problems, and it's doing everything that the classical vision pipelines are doing, but it's adding the uncertainty quantification. All right, so that tool has been just extremely useful for us in this problem, and also the bandit problems and a range of other problems. Okay, so you can find pointers to papers on my website if you're interested. Okay, so I'm going to finish up with just a couple of quick comments, and then I'll be happy to have more of a Q&A. So just return to the bigger, higher level picture here. I don't think that the current era is really AI in the sense of putting thought into the computer, making it think like us. I mean, that's going to happen someday, maybe in 100 years. But right now what we're doing is we're building real world systems that take in data, and they help make decisions, and they link huge numbers of people together, and they put us linked to things in the real world, like restaurants or factories or transportation or finance or entertainment and all sorts of things. And we're being linked to these things in new ways. It's not just the bits being streamed across a wire, but it's about the preferences, it's about the uncertainty, and it's about the interactions among people and the trade-offs. So if you go back historically, I think that what this is, it looks like the emergence of a new engineering field. So in the 40s and 50s, there was no chemical engineering in the 30s, but there was already fluid mechanics, there was quantum mechanics and chemistry. So you knew what would happen when you put molecules together in a small, test tube. But the idea of building a big factory in a field somewhere and having it produce products, that was not, no one knew how to do that. And you had to develop new thermodynamics and new principles of fluid flow and so on. And a new field emerged called chemical engineering that took, several decades to emerge to allow you to build such systems in a trustworthy, reliable way. Same thing with electrical engineering. Before there was electrical engineering around, 1880, there were already Maxwell's equations. So the whole phenomenon was understood. But the idea of bringing electricity to a city or lighting up a person's home or building a circuit and all, you had to have new principles emerge, and those principles became called electrical engineering. And it took, again, a couple of decades for people to start to build these things and then develop the principles. I think that's what's happening in our current era. We have some proto-principles of statistical inference and computational algorithms, and we put them together with gradient descent, and we build these kind of ad hoc systems that on a small scale we think we know and understand, and then on a big scale we don't really know. We hope they'll work, and sometimes they seem miraculous, like a factory in the field that just suddenly produced chlorine, but in other cases they have biases, they have troubles, they are failing, they aren't going to work if you run them for a few years. And so we need a new engineering field. And to me, this is exciting because the new principles are going to have to emerge, and I don't even know what they are. But I do know one thing, which is that they need at least the contribution of foundational ideas from computer science, from statistics, and from economics. And it's kind of interesting that all three of these disciplines have interacted in pairwise ways in the past. So statistics meets computer science, that's machine learning. Computer science meets economics, that's been called algorithmic game theory. And statistics meets economics, that's called econometrics. And roughly speaking, each of these pairwise things doesn't have much to say about the third leg of the simplex. So, econometrics doesn't have a lot of computational mechanisms in it, not a lot of, combinatorics or whatever. Algorithmic game theory has very little statistics and learning in it. And machine learning up until, recently has not had a lot of economics in it. And these are all not entirely true, but they're mostly true. And of course, the real point is that emerging problems blend all three. And I mean emerging problems out in industry, emerging problems that people care about as we start to build these new kind of systems, And so I'm very, I don't know what to call this new emerging engineering discipline, but I personally think that AI is a terrible term for it because AI brings back the baggage of the Turing test and the thinking computer, which is not what we're really aiming at here. So anyway, that's the end of my talk, and I'll be happy to stay on for a while and ask and talk with you folks.
Thank you, Mike. That was a really fascinating talk, and I'm sure there are lots of questions. So let me hand it over to Manish and Guhan.
Right. Thank you, Mike. Thank you, Mike. This is really, really very interesting. Chandramurthy, you have a question? Please go ahead.
Yeah, thank you, Mike, for such a wonderful talk. Just curious to know if maybe probably approximately correct learning is a special case of this uncertainty quantification that you described, or how do you see the
No, it's not. I mean, so first of all, for me, probably approximately correct is basically empirical process theory from statistics. Okay. And the only difference is that it adds the computational side. It says in polynomial time. Everything else about PAC is old from statistics. What was new in Valiant's work was in polynomial time. And that's been true of a lot of machine learning. It takes ideas that were already present in statistics, kernels and, and bandits and, and causal inference and, you name it. And it adds, computational dictum, that it, be fast. And statisticians didn't care about that so much. They were working on small problems. But every area in statistics and including PAC inference worry about uncertainty. If you don't do that, you're not talking about learning. But the kind of it I'm talking about is after gathering the data. PAC guarantees are before gathering the data. They're an a priori statement that I will guarantee you that with high probability, this estimator will work on this class of problems before I see any data. Okay. These kind of uncertainty quantifications are after you see the data, put a confidence interval on something. Tell me how sure you are of some decision. That's not what PAC does. That's what confidence intervals do.
Thank you.
Amrit, would you like to unmute yourself and ask a question?
Sure. I hope, Mike, you can hear me, right?
Yeah, I can hear you.
Yes.
Yeah, sure. So this is a question which I had pre-planned for the talk, and thanks for such a wonderful talk. Like me being around 1.5 years in industry and just getting started with machine learning, it's kind of not clear where the field is moving and what should I focus on, right? Should I focus on theoretical aspects or more on the engineering side of things and stuff? So it's kind of not clear where the landscape is right now. But yeah, this was to give some background to the question. The question more of is, as you mentioned, like that AI or whatever the field is called, which is kind of built on statistics and then economics and then computer science, right? And which we are calling machine learning right now, right? And you also mentioned this in one of Lex Friedman podcasts as well, right? So if this field which you are talking, and in Lex Friedman podcast, you mentioned that the conversations we are having right now for intelligent machines to have that conversation, it is a centuries away problem, right? But then seeing advances with chat GPT and stuff, do you believe like we as humans kind of underestimate scale a lot, as in we will never be, due to our cognitive limitations, be able to know what will be it like to process entire internet information? And some people like Demis Hassabis, they claim that the next Nobel Prizes may be the average of internet scrolled. So do you believe like the intelligence we have captured as humans because of our evolution and genetic evolution, that can be compensated by scale with AI?
Well, no, but let's be clear. I mean, a computer can already do many things that you and I can't do, right? It can calculate the digits of pi out to 1,000 decimal places. It could do integrals. It could do all kinds of things we can't do. And that'll continue. I mean, it also, the search engine organizes the internet. You and I couldn't sit down and do that. The finance system is run, on computers, air traffic control, there's all kinds of things computers can do that go beyond what we evolved to do and what a human does. So that's not new, and it's good. That's what computers should be doing. It's augmenting us and making us different. Chat GPT, I mean, I think, and things like, vision generative, models and all that. I think what's most interesting about them is that, at some point, people do creative things with them, like new kind of, movies will be made, or new kinds of sounds will be made, or new kinds of, things will be created. That's kind of like the art side of it. That's what people have done with technology in the past. And I think that's kind of interesting. And then people will find new business models for them. And it'll start to be a different part of our culture, that some of these entities exist and they could do things that we never did. Okay. That doesn't mean they're intelligent. Okay. The search engine is not intelligent, really. In some, it's just indexing websites, but it makes us way more intelligent as a society. It makes each individual more intelligent because we can look up things really fast. Right. And so, high interacting, maybe translating systems that can go from, Mandarin to English really fast. That's kind of changes our world, but it doesn't mean the system itself is intelligent. I don't see that ChatGPT is intelligent. And in fact, despite, if you gather, billions and billions and billions of sentences and you kind of stitch them all together, and it's done with gradient descent, it's kind of cool, but not entirely surprising that it comes out with coherent looking stuff, because there's all this coherent looking stuff that's been as part of its input. That's not to diminish that there's things that are looking even more than cool, but I don't see in that an understanding of the world. If you have a real conversation with a real human over days, you'll start to build up a mutual understanding. You'll have a mental model of what you're talking about. Here's some social sphere I'm talking about, or some trip I'm taking, or some interactions I'm planning, or some, here's what's happening in my life and all. You'll start to know a human from a ChatGPT. I think that'll be true for the rest of our lives, because we build a mental model, and ChatGPT is not building a mental model. Okay, it's just, in some sense, pure statistics, and it's surprising how much statistics can do. It's like an amazing show, just like it's a beautiful show to have generative images that we've never seen before. But I do not personally believe that that's the road to. Suddenly it'll emerge that those systems are as smart as humans. I just don't see it at all.
What is your take?
Why we should really care? We have a lot of humans that are really smart. Wouldn't it be cool if computers did other things like, the steam engine did, or like the search engines are doing, or like, translation systems are doing, that take humans and allow us to be happier, more safe, more empowered, and all those things. Having a system that I can sit and it pretends to be a human and it's just as good as a human, or even maybe even smarter than me in some ways. I don't know. I'm not sure I see certainly I don't see the economic value in that.
Sure, thanks. I just want to follow up on it. What is your take on the statement like Demis Hassabis made in Lex Fridman podcast, that the next Nobel Prize can be average of the internet scrolled? And then they kind of argued that
it'd be what? Sorry?
The next Nobel Prize could be average of the internet knowledge today, like, because we as humans are kind of multidisciplinary in one nature, but then it is not possible for one human to have knowledge of all disciplines, whereas that is possible for current systems to do.
Maybe it just doesn't excite me in the same way. I mean, who cares about the Nobel Prize at some level? It's a prize that humans created for humans. Right, it recognizes a certain moments, like discovery of structure of DNA or something, and it's kind of for humans to recognize that humans did these things and to motivate, incentivize other humans who are younger to want to do things like that. One shouldn't give it a mystique beyond what it is. It's just certain. There's been billions of scientists, and some of them have done miraculous things. The Nobel Prize winners are a little subset of that, and they're not everything. And if putting knowledge together in new ways with a computer kind of comes out to some new knowledge, that's great. But it didn't. Why do we have to think of that as so striking that it deserves a Nobel Prize? I mean, again, deserves a Nobel Prize. I don't even know what that exactly means. So I'm a little puzzled by that question as a scientist. Yes, I want to have computers help us be happier, more entertained, safer, more wealthy, make our children happier, have human life be better and more understandable and all that. And if Nobel Prizes and other kind of prizes help motivate humans to do better, I mean, we're kind of making a mess of our world right now, and I want prizes that make the world better. If computers can help us make the world better, solve some more problems, and then open up some new opportunities, then that's great. But I don't see that magic is going to happen. I just think we're kind of in an era where we think that computers are suddenly going to because they can do AlphaGo and they can, do things that we can't do easily. That's going to turn into something kind of a superhuman magical capability that takes away the interest in being a human being.
Thanks a lot for the perspective. It was really helpful. Thanks.
Okay.
Professor Papiraju, please go ahead.
Hi, very nice talk. Thank you, Dr. Michael. One question, I really like the triangle at the heart of the new emerging engineering discipline, and wondered how cognitive science fits in. You have, we have to, when we factor in people, we bring in their cognitive biases, their dynamics of what they are thinking, their emotions, what their past, their culture. Currently, I don't think economics deals with all aspects. I mean, this is like the interface of sociology and economics, perhaps. And cognitive science as a discipline is trying to look at all of this and see the impact on human decision making. And do you see a role for that? I know that you started out your journey from CogSci.
Yeah. Let me just be direct and honest, maybe because I'm a certain age. I think cognitive science is moving extremely slowly. And because it's posing the most difficult problem there is like, how does the mind work? And I don't think in the 40 years I've watched it, we've really made hardly any progress in that. Even like, how do we move our eyes, to focus on something is still very hard to understand. I think what you're really asking is actually about behavioral economics, which is that, if we study real people who really behave in, interactions and trades and, social situations where there's value to be passed, they don't act like, rational agents. They have all kinds of imperfections. They perceive things in certain ways. They have to be motivated and et cetera, et cetera. And behavioral economics is the field which studies that and runs experiments and does it. Cognitive science mostly has been about the individual human sitting in a laboratory, making decisions and based on something on the screen or doing memory and so on. So it's studying the individual human. And again, as you hopefully have seen from my talk, I'm more interested in the collaborative, bringing everybody together, having a social science kind of side to our field than I am in trying to put, a lot of cognitive strength inside of the computer, inside of a single individual, be it computer or human. Now, of course, I'm not trying to put walls up here. Good cognitive science contributes to behavioral economics, which contributes to economics, which contributes to computer science and all. It's all together. But just if I were to tell my child which field to pick on, if they're really interested in the human side, I'd say behavioral economics by far compared to cognitive science.
Right, thank you.
Professor Chiranjit, would you like to go ahead and ask your question?
It's more from my colleague, Professor Devdutt Dubashi.
Hi, so this is about the slide, the vignette about the two-sided markets with the agents and the bandit arms. So normally it's the agent who's active and chooses one of the arms to play, but in your version, the arms were active agents too, because they were picking one of the agents to respond to or to prefer. So then in that setup, so you had regret only from the side of the agents picking the arms, but like there's probably regret from each arm about which, what it got from. So it seems like a richer problem with some kind of a multi-agent and many different kinds of regrets and some kind of, it should be treated as a multi-agent regret problem.
Yeah, you're absolutely right. And now you're getting into the real richness of the field. First of all, in the classical matching setting, you had pessimal regret and you had optimistic regret. And, there was two sides. You'd match like the dating situation, marriage, right? There's the men on one side and the women on the other side. And one model is the men get to propose to the women and the women only can accept or not, right? And as you may know, under that model, the welfare of the men is very high and the model of the women is very low. There's a stronger, nicer thing to say. If you flip it around, of course, it's the opposite. And then people have worked on other things that kind of get a little blend of the both, and it's not so clear. And it's a whole thing of its own. And you're absolutely right here is that we want to have the overall social welfare be high. We don't want to focus on one side or the other, and we really want to have both sides be adaptive. And we have to kind of make some trade-offs. So sometimes this is called Pareto optimality, right? There's, no one's entirely happy, but you can't make anybody any happier, things like that. And this is the real world. You're not going to just have a top-down, centralized government decision-making system or a Silicon Valley decision-making system that makes everybody optimized, right? So we have to accept these trade-offs and imperfections and sort of being able to formalize them and being transparent on who's winning, who's not, and then letting you be opting in or opting out. That's all part of it. And then also being clear on what regret and who's to regret and, based on what oracle and based on, what's obtainable and all that. I think, other metaphors are helpful. Like think about the banking system. My grandparents weren't used to like credit cards. They just couldn't believe that this is appropriate to give a card to somebody. And previous generations weren't even used to money. And then humans got very used to it. And we got used to interacting in these ways. And with privacy, we kind of now have this unsure, how much privacy do we want? How much are we giving up? We need to quantify all that. And our children's children will quantify those things, I think. They will expect certain things out of interactions that we don't expect. They won't go on the internet just blindly hoping that everything is okay. They'll expect certain contracts to be set up. They'll expect to have clear benefits and losses and all that. So we're groping towards that. And so part of this is indeed the whose welfare and who owns the data and who gets paid and all those things. We're not at the very beginning of talking about that. And when I say we, it's not like you and me and the technical people. It's all of the real people. It's the social scientists too, and the lawyers and the politicians too. Everyone's got to have to be involved in it.
Thanks a lot.
So Professor Jordan, we are, I think, at the end of the Q&A session. So if you have any final thoughts, maybe you can add. Otherwise, I'll ask either Manish or Manik to take over.
No, I don't have any final thoughts other than just, I really do like being networked to everybody in the world. It's not just that I believe it as an academic exercise. And so giving a talk like this is an opportunity to really exercise these networks that we're all building up. And I really do want to encourage all of you to think about the social side of what you're doing and not just like the ethics and all that and, trustworthy and robust. But think about your real goal here is not just to build smart machines, but to build machines that interact well with large numbers of human beings and really, really take that seriously. I think that's really critical. And also remember that all countries and all parts of the world are going to be doing this. It's not like one group of people can or should own any of this. It's really a collaborative endeavor throughout the world. So that's my parting thoughts.
Cool. Thank you so much, Mike. That was a really fascinating lecture. And I think it's motivated a lot of us to think in new directions. And of course, we look forward to having you be physically present and later on this year and listen to you again. So thank you very much. Take care, everyone.
All right. Thank you, everyone. Goodbye.